Okay, guys, we're going to take a look at some elemental cycles. And I hope as we go through these last few slides, you're noticing some parallels. Throughout this entire module, we've talked about respiration and fermentation. We've used tools in the laboratory to be able to tell if organisms had the metabolic capacity to perform some of these pathways, which basically meant they had the enzymes to do those things, right? And what we're doing now is we're going to look closely at certain of those very common elements, those like carbon and nitrogen and so on, to watch where they go as all of these really complex metabolic pathways take place. All right. So the first cycle is the carbon cycle I'd like to look at with you. And the thing about a lot of the pictures that you see in textbooks when it comes to these cycles is that they are not simple. All right, so I'm going to show this is from a textbook I used just previous to the one you have, and yours isn't any better. Yours is more complex, the online text. So I thought I'd stick with this one, and then I'll show you my version that kind of simplifies the overall ideas and gives you something that you can study and hopefully remember, right, for the next exam. All right, so if we check out a very simple version of carbon. So let's take CO2, right? CO2 is in the atmosphere, a certain percentage, and it is going to need to be harnessed to go into molecules that we have on living things on Earth, right? So all of the different organic molecules have carbon. Where are we going to get it from? Well, CO2 is out there. So if we look at plants and other green photosynthetic organisms, and many of these organisms are in the ocean. I think I alluded to that in the last clip, right? These organisms are going to be able to perform photosynthesis. They're going to take CO2 and water. So I have the equation down at the bottom of the slide here, okay? And they can take this photosynthesis I have in the yellow arrow down here towards making glucose. So it's basically turning aerobic respiration on its head, right? And we're going to be able to take carbon and fix it into a more complex molecule like sugar, like glucose, okay? So if we look at carbon fixation, a common way to do this would be through photosynthesis, taking a simple CO2 molecule and water and transforming it using the energy from the sun's rays, right, to form bonds to make this bigger 24 atom molecule called glucose. Okay, so we have these photoautotrophs, right? All of these different sections of module 2 are combining here, you see. So this is a way of fixing that carbon on Earth, right? Now once this is done, so let's follow this fixations going on with trees and plants on Earth, right? And then of course those plants can assimilate and use those sugars to make much larger macromolecules, and you get, obvious plants and trees and all of that, right? But it's also true that animals can feed on those, okay? Of course, you're going to have animals feed on these, and all of these organisms, whether they're animals or plants, or whether it's bacteria that are using the sugars, they are going to respire, okay? So here you have respiration going on from animals. Plants also respire. And of course, soil and water microbes also undergo respiration, all right? That's how they get their energy. So what is that? Well, if it happens to involve oxygen, we would have glucose and oxygen And then aerobic respiration would take place, like you see down here under this orange arrow, and we have our CO2 back again, right? This completes the cycle, right? Imagine if all of the carbon pulled down to this earth never went back into the air, right? I mean, we survive because of what's in the air, right? Because this give and take is constantly going on, all right? So we have cellular respiration versus carbon fixation, kind of two diametrically opposed things going on. Now, it's possible for dead organisms, dead plants, dead animals, to not be decomposed, and that's a big part of respiration too, is all of the soil and water microbes that basically feed on dead animals and plants and so on, okay? And these would respire. But it is possible for those dead organisms to collect and to stay on Earth for a while. And these might be known as fossil fuels, right? Charcoal and oils and things like that. These are basically organic material that has yet to be returned to the air, right? And sometimes, of course, we use some of these organic materials, whether it's wood from trees or whether it's fossil fuels that get trapped underground, and we return that to the air by burning it, right? By basically heating my house, I am going to very quickly break down all of those organic materials. So we have, again, a return to the air there. We have a cycle that is completed, okay? So let me show you a version of what I like to do with all these arrows, because this is just a mess, okay? So let's take CO2. CO2 is a really simple molecule in the air, okay? And what we want to do is bring it down to Earth, right? So we're going to have autotrophs. If they're using the sun's energy to bring this inorganic carbon down, then we can say they're photoautotrophs. But definitely something they're doing is a carbon fixation process, right? And when they fix it, they're going to have some kind of organic molecule. In the case of photosynthesis, this would be a glucose molecule, right? But it definitely is an organic molecule. And it's true that some organisms can do this and they make methane out of it. In fact, we talked about anaerobic respiration taking place with a carbonate molecule, right? So it's very similar to carbon dioxide. Carbonate is. It's just got an extra oxygen and a negative charge, okay? So those anaerobic respirators can also perform carbon fixation, okay? But let's just keep it simple for now and think about this being photosynthesis process. All right, next we have the assimilation and consumption of those organic molecules, okay? Assimilation meaning the plants will use that sugar, change it into other organic materials, proteins, right? Lipids, nucleic acids. They'll pull the minerals out of the soil that they need, but everything else is coming from the air, okay? Also, you might think about the bacteria that might be utilizing some of these organics, the animals that would eat plants, right, and utilize that organic material, okay? Now, all of these living organisms, the bacteria themselves, the animals, the plants, they all are respiring. They're all going through some kind of respiration process. A lot of them that we think of, like for humans and other animals, it would be aerobic respiration. And aerobic respiration gives us back that CO2, right? So if an animal is going to break down glucose, for example, using oxygen to do that, it's going to break those bonds and CO2 is going to be breathed off, right? And this would be true of a lot of bacteria. It would be true of plants as well. Now, what if these plants, animals, bacteria die? Well, decomposition, which is primarily performed by bacteria in the soil, Well, those bacteria are also respiring, right? So even if these larger animals, plants, and so on pass away and die, all of those molecules are being broken down, and the CO2 from the decomposing bacteria that are decomposing those dead organisms are going to return CO2 to the atmosphere as well. All right, finally, if we considered some of these plants, animals, some of this organic debris, if it were to be trapped underground or trapped at the bottom of the ocean or something like that, we might find that there would be fossil fuels, okay? And these fossil fuels could sit around until at some point they could be burned, combustion, right? And that would also return CO2 to the air. Now, a lot of the CO2 in the air is what we're worried about, by the way, right? When it comes to global warming. It happens to be a greenhouse gas, which means that it traps heat from the sun. And the more CO2 is in the atmosphere, the more problematic this climate change is going to be. And this is why we're trying to get away from fossil fuels, though we can't do it overnight, right? I mean, we're really dependent on these fossil fuels to heat our homes and to get energy for other things. All right, so this is my kind of breakdown on the carbon cycle. Okay, one way to study for that second exam. Okay, what I also added here were a few stars just to show you where bacteria are really important, where they're really playing a big role. All right, now let's check out the nitrogen cycle. Now, the nitrogen cycle, if you can believe it, is even more complicated. A lot more new terms that we need to get down. So let's kind of compare it to the carbon cycle, see how it's similar. Okay, with carbon cycle we had CO2. This was a simple inorganic carbon molecule in the air we could use. Now, mind you, I should say we can't really use it to make sugars, but anything green can, right? Any plants can. So we are completely dependent on those organisms. All right, so for nitrogen, well, there's N2 in the air, really abundant. A good 80% of the gases in the air are nitrogen molecules. Now, if we look to see, is there anything similar? And I find a fixation part of this diagram, and we had carbon fixation, we're going to have nitrogen fixation. We're going to have this free nitrogen gas, okay, this N2 in the atmosphere. And organisms on Earth are capable of fixing that nitrogen, chemically changing the N2 molecule, okay, into other molecules like ammonia. And the organisms that do this are entirely microbes. A lot of soil bacteria do this, okay? So almost exclusively bacterial activity, okay? Now, these prokaryotes then fix the nitrogen down to ammonia, and, well, plants and animals can't really use ammonia in that chemical form. However, other bacteria can. So we run into organisms that happen to have a prefix in their name that says nitro, for good reason. They're really active within the use of nitrogen-containing molecules in the soil. Some of them make nitrites out of ammonia. Some of them go on to make nitrates. And nitrates are basically fertilizer for plants. So again, almost entirely bacterial activity in this cycle going on so far. Now at this point, the nitrates can be assimilated into plants, and the plants can use those nitrogen-containing molecules to make their nitrogen-containing molecules, like we know proteins and DNA and stuff like that has nitrogen in it. And of course, other animals can come along and eat those plants, right? So just like we saw with the carbon cycle, we have this assimilation process by plants and then other things that eat those plants. And of course, any of those organisms could die, right? And those molecules could be broken down back into the soil, okay? And so we have this idea that there would be a decay, a decomposition again, right? And that decomposition oftentimes leads to ammonia again. So we can stay down here in the soil with this decomposition and then a breakdown by bacteria and then a assimilation by plants. And this is basically what using manure and using compost does for us. We take the old, dead, decaying, decomposing materials and we put them back in the soil, right? And we get some nice healthy plants again. But we also have some bacteria in the soil that are known for their ability to take nitrates and go quite the opposite way. They're not fixing nitrogen from the air, they're going the other direction. They're going to denitrify. These are called denitrifying bacteria. They take nitrates to nitrites and ultimately to make N2 again, which goes back into the air. Again, N2 is the most abundant molecule in the atmosphere, but it wouldn't be if all of the organisms that assimilate that nitrogen into their organic materials like proteins and nucleic acids, if they weren't broken down and returned. Okay? These cycles are not only do bacteria have bacteria led to our existence, and they have something to do with an evolutionary trail, right? But they also are currently making our world so that it is habitable. Okay? A lot of times we as humans will do things on this globe that change the abiotic environment, and we really don't consider how it's going to change the microbial world and how dependent on that world we are. Okay? So let me show you my simplified version, and it looks kind of similar to the carbon cycle, but let me show you my simplified version of the nitrogen cycle. So this is my breakdown on that. So let's start simple, like we did with carbon. N2, simple inorganic molecules sitting out there in the atmosphere. We need to fix that in a version that can be used on Earth. So nitrogen fixation, just like we had carbon fixation, we have a process where in this case we make ammonia. Okay? Now I say we, of course I really mean all the bacteria in the soil. All right? Now ammonia is not utilizable. It can't be used by plants or ourselves to be put into proteins and nucleic acids that we need. So there are a whole other set of bacteria that will go on to nitrify, take this ammonia, change it into nitrite, and ultimately into nitrates. Now once we have nitrates, well, unfortunately animals still can't use it, but plants can. Okay? So this is a natural fertilizer for plants. These plants will assimilate, grow bigger, and now animals can eat those plants, right? Now, animals and plants can also return nitrogen-containing molecules to the earth, either through excretion, right, when we urinate or sweat. We are returning a nitrogen-containing molecule. It's actually urea, but if you've ever checked out, a diaper pail after a little while that hasn't been cleaned, you'll smell the ammonia, and that's basically a breakdown product of urea. But we also have this decomposition idea again, okay? This idea that when plants, animals, bacteria, living things die, well, there's a whole host of decomposers, mostly bacteria, that also help to return ammonia and other nitrogen-containing molecules to the soil for other organisms to use. Now, this cycle would not be completed if we couldn't get back to nitrogen again, and this is where the denitrification type organisms come in, and these are also soil bacteria, by the way. So this one, what I want to kind of focus on now is where are all the red stars when it comes to the nitrogen cycle. In other words, if I were to put a red star on every process where bacteria are involved, where would they be? Nitrifixation, and I should put an exclamation point here. I put exclamation point here. Almost entirely bacterial. Nothing else doing this for us, okay? Nitrification, again, almost entirely bacterial. Decomposition, almost entirely bacterial. Now there's some fungus that will do this. Some decomposition is performed by other microbes, but certainly mostly microbial activity, and a lot of it is bacteria. Okay? And then finally, denitrification, almost entirely bacterial activity. So, yes, we are dependent on our air around us staying pretty much the way it is for us to survive, and this is we owe this fact that the nitrogen is replaced, and the fact that we can pull it back down to all these bacteria. Okay. And one thing before I leave this nitrogen cycle here, I have an interesting kind of quick story for you. For years, we've been making our own fertilizer, right? I mean, when we grow plants, when we grow crops, we basically are taking advantage of the fact that these bacteria have fixed the nitrogen and made nitrates for us so that our plants will grow. But then we take those plants away from the soil, right? So we're basically, if we continue to do this, we just take more and more of the nitrates from that soil, that plot of land, okay? And so at some point, it has to be returned. And one way to do that is to produce our own fertilizer. But this process, where we take nitrogen, N2, and make ammonia and finally nitrates out of that nitrogen-containing molecule, is a very expensive industrial endeavor. Okay, really expensive, and it can be very dangerous. So you might have heard of there's a factory that exploded in a small town in Texas a couple years ago. That was a factory for fertilizer. It's a really dangerous process, but it's an important one because this has allowed us to grow crops and feed the world. Okay, so one little story that I really don't want to spend too much time with here, but I'm going to include a link in underneath the YouTube video about, I think his name is Fritz Haber. Okay, Fritz Haber was the man who figured out how to harness this N2 and to make fertilizer, basically, he got it started. And he has a really colorful history. He was a German scientist, chemist, and a Jewish man. And he played a big role during the World Wars. And not always what you would probably consider a good role or an ethical role. But he played a big role in feeding the world in his investigations into how to produce ammonia from nitrogen. So I'll include that link, and you might want to check it out, okay? Okay, the last cycle that I'll mention is the sulfur cycle, and it's similar to the other cycles in that there's a certain amount of sulfur contained in the air around us. Some of them are sulfates. And we have bacteria in the soil that are capable of going both ways, fixing that down to Earth and releasing it out into the atmosphere as well. For this cycle, I'm not going to get as much in the details, and I wouldn't worry about me asking you those details on the exam either. I'd say know that there is a sulfur cycle, but concentrate on knowing the details of the carbon and nitrogen cycle. Okay? And I think that's about it. We're going to call it quits for Module 2. Halfway through the lecture stuff, guys. Stick with it. I know it's tough. A lot of stuff in 5 weeks, but remember, it's a 15-week class, and we'll find an end to this tunnel soon. Okay?